Good morning, good afternoon, depends on where you are. Welcome to participate in the webinar. Today's webinar is called IoT Fundamentals, Everything About LoRa. I'm your presenter, Jessica from the Marketing Department of MileSite. In this webinar, let's talk about some fundamental knowledge about LoRa, such as the advantage, use case, architecture, the difference between LoRa and LoRa 1. And we will also cover some very important technical terms. And there are functionality, something about LoRa modulation, demodulation, restrictions, the range that are so important to know, okay? Why LoRa is so popular? But first, I think there are 10 reasons that make LoRa 1 really powerful. And you can also find these characters in some other LP1 technologies. But with this kind of combination, LoRa 1 becomes awesome. Such as the super low power consumption, it means ultra long battery life, and long range. And LoRa uses the license-free. It uses the license-free spectrum, so you don't need to get any approval. You don't need to pay any license fee to deploy a LoRa 1 network. And the geolocation helps the network to find where is your device, no matter it's indoor or outdoor. And you can build up your own private network or the public LoRa 1 network with the same sensor, with the same gateway in the same open source software LoRa 1. And also you can seamlessly handovers from one network to another and don't need to worry about the security issues because there are levels protection over the air. And finally, there is a very, very large ecosystem that composed of the device makers, gateway manufacturers, network service providers, as well as the application developers or engineers. So once you take use of LoRa, you can enjoy all the benefits, all these kind of advantages that bring by LoRa 1. And also you can work it in smart agriculture, in the environment monitoring, and you can use it to measure something for nature disaster prevention, such as the COVID-19 pandemic vaccines monitoring, okay? And also you can use it for the monitoring of industrial sites of a long range. So LoRa 1 is also really powerful in smart city use cases, smart buildings, and also obviously can be widely used in the supply chain. And there are many, many different use cases in LoRa 1. So the versatility makes LoRa 1 really powerful. So you can use it in many different verticals and areas. And LoRa is really a global technology, so you can use LoRa 1 all over the world, either in the public network or in your own private network. So everywhere there are regulations with a license-free spectrum that you can find the license-free unlicensed bands and take use to work LoRa. And why does a LoRa 1 network architecture typically look like? So this is a diagram. In this picture, on the left side, you can see the end nodes, end devices. They are connected to gateways. Actually, there's not really a connection between the end node and the gateway because the gateway is basically listening for the messages from end nodes. And the gateway is a dumb packet forwarding device. It doesn't understand the contents of the packets from the end nodes. And the gateway cannot decide what kind of message or what comments to send back to the end nodes, because the network server does this kind of things. So the network server identifies the end devices. Network server receives multiple copies of the transmitted packets, and network server decrypts and deletes the same packets. So network server does some security stuff to protect the data and then forwards the payloads to whatever application server the end users require. And finally, you have the application server here. This is the final destination of data, where you can get your data, where you can manage devices, where you can check the status, where you can send the message, you can send the comments back over the internet through gateway to the end nodes. So that's the complete the LoRaWAN network architecture here. So what does the difference? What's the difference between LoRa and LoRaWAN? First, I think LoRa is the physical layer. It's just a radio technology. It's developed and maintained by some tech company. So here you can find the logo of the some tech corporation. And LoRaWAN is an open networking protocol. It's a protocol that delivers the secure bidirectional communication. It delivers mobility and localization services. So LoRaWAN is standardized and maintained by the LoRa Alliance. And in this slide, in this picture, you can find on the layer below, in the green color, you can see the different regions have different bands, such as in Europe, in United States, in Australia, in China, and there are different frequencies. And then there's a lot of modulation. I think you must be familiar about FSK modulation or ASK modulation, but here we're taking use of the LoRa modulation. And LoRa modulation is really about transmitting data over the air in a very efficient way over a long distance. So that's LoRa. That's really just getting data through the air. So that's the work of LoRa. That's the job of LoRa. Then in the yellow part, that is what LoRaWAN does. That is the MAC layer. It means Media Access Control Layer. And in this layer, it does all the security features in LoRaWAN. And you can activate devices on a network. You can count acknowledgement messages. You can synchronize the windows that your application can send the data, can send a comment back to the end devices. So LoRaWAN is here, looks like a bridge that can help you to send comments, send messages back to the end devices. So to realize the bidirectional communication and things like that. So if you need the payload encryption, decryption, the security part is also responsible by the LoRaWAN. And then on the top, in top blue, that you can find the application is the IoT application layer. So totally, you have the physical layer, you have the MAC layer, and also you have the application layer. And what is LoRa? Well, I think LoRa is really complementary to our existing IoT communication technologies. It's long range, but obviously at the cost of bandwidth. So LoRa is designed for IoT use cases, which require only very little bandwidth, very small data. That also makes LoRa really suitable for the devices that are usually in sleep mode. So device can basically be in deep sleep mode at most of the time. And it just wakes up when a message needs to be sent and then goes back to sleep again. In this kind of working mode, well, you can take use of LoRa to extend battery life if your devices are battery powered, not the like DC power or solar panel powered, but is the battery powered. In that case, battery life is so much important. And LoRa can be used in the license-free spectrum. So in every country, government provides some license-free spectrum for the industrial, for the scientific, and medical research use studies. Okay, and the license-free spectrum is not globally unified, is not globally harmonized. Different from Wi-Fi, different from Bluetooth. There are 2.4G, 2.4 gigahertz or 5 gigahertz that is globally harmonized. But LoRa is not in that case, unfortunately. So if you visit China or if you visit Japan, you don't need to modify anything, any settings in your mobile, but you can directly take use the functions, take use of the data transmission, send a picture, or send a email by Wi-Fi, right? So, but LoRa is different. With the sub-gigahertz frequencies, LoRa, that means in different regions, you have to use different frequencies. For end users, I think they don't really have to think about this because LoRa 1 has been supported in more than 150 countries, where they can find all the frequencies for their own region. But if you are a solution provider, if you want to ship devices to different countries, or if you want to deploy solution in different regions, please choose the right version with the right frequency because it's decided by the hardware, by the LoRa chipset. You cannot change it through the firmware or software upgrading. So you can find from in Europe is 863 to 870 megahertz, and in China is CN 470 to 510 megahertz, and in Australia is a little different from the frequencies in United States. So we need to be mindful about that before placing our orders, okay? And as we all know, LoRa uses our chop spread spectrum modulation. Modulation means how the analog or digital information are encoded onto a carrier signal. So actually, this chop spread spectrum modulation is also used by some other animals, such as the whales, the dolphins, the bats, and how they communicate with their friends or with their families, and how they hunt their food or their prey. So they use chop spread spectrum. And this also works over very long distance. So that's where the chop spread spectrum comes from. It's from our nature. And the main characteristic of LoRa modulation, I think there is a bandwidth in which the communication symbols are modulated. So there is a center frequency, and around that center frequency, there are symbols modulated. And here you can see on the right picture in the spectrogram. So you can see those modulated symbols. And the bandwidth is quite high. It's typically 125 kilohertz, and that makes it different from the narrowband waveform here. Because the narrowband waveform, which choose a center frequency and then use that single frequency to send data. So the narrowband signal is suppressed when transmitting spread spectrum. So the spreading waveform makes LoRa reduce to interference here. Because here you can find from the LoRa spectrum, this spectral program, you can find in a typical bandwidth, I mean the 125 kilohertz, how to sweep the LoRa frequencies at every frequency point during the transmission. So even if there are other signals occur, even there are other noises occur, because of the spread wave, LoRa can still recognize the right message and receive it. So here you can find the noise level. Noise level, it means where is the place that full of your unwanted, your unwanted interference signals, which can corrupt or destroy your symbols. But here you can find LoRa can still working normally under this, below this noise level. So that's one of the unique point, very unique characteristic of LoRa modulation. And here are some comparison of unmodulated signal and modulated signal here on the right corner. And for example, when an end device sends a message, sends an uplink message, it sends some up chops and then down chops, and again more up chops. What's that meaning? What's the meaning of those kind of chops? The first, for example here, the first 4 up chop symbols, there are preamble symbols that used to detect LoRa chops, that used to log LoRa frequencies, okay? And the next 2 down chop symbols, there are timing synchronization symbols that are used for the timing synchronization, so it can tell the receiver that we need to work at the same tempo, and then followed by the 4 modulated symbols again. So I mean the payload. So you can see the jump in the frequency. That means payload. And I think this whole process here is like an indication, is like an announcement for the receiver that there is data coming, so you need to get prepared. I want to send you something. And what does the payload mean? Well, for example, if you hired a driver to deliver apples for you, well, the weight of the driver is load. The weight of the car is load. And the weight of apples are load as well, right? But for you, only the weight of the apples is the payload. That is, you really need to pay for it. So that's the payload meaning. And on the modulation side, if we have the LoRa modulation, of course, there are demodulation side on the receiver side. So the inverse happens. So the LoRa demodulation will figure out what the symbols were transmitted by the sender. So for example, here the code encodes 8 preamble symbols and 2 synchronization symbols and 100 information symbols to LoRa chop, and successfully decodes. Then you can find the codes generates the pros here in the picture. So you can find those bright small points. There are payloads, okay? And please pay attention here. The sender and the receiver, they can be either end device or gateway in LoRaWAN network. This modulation and demodulation, they are so simple to work. So you can find the radio module in both devices. So that means it can also be carried out by the end device and gateway. They can realize the bidirectional communication. And bidirectional communication also makes LoRa unique, you know. LoRaWAN-based network is made up of 4 important components, 4 important parts: the end device part, the gateway, the network server, and finally application server. So the end device sends data to gateway, that is uplink, and gateway pass the message onto the network server, which in turn passed message onto the application server finally. So that is the uplink process. And additionally, you know, if the network server sends the message back, either for the network management or on behalf of application server through the gateway to the end devices, this process we call downlink. So that's very important to be mindful here to understand what is uplink and downlink. And gateway can listen to multiple frequencies simultaneously. So in every spreading factor at each frequency. So this allows gateway to handle multiple devices at the same time with bidirectional communication. Then in LoRa, there's another very important term, that is the spreading factor. I think the best signal occurs when end device and gateway, they are in very close distance. But as we have seen, the signal fading or the attenuation increases as the distance increases. So the power of the received signal becomes unusable finally. This could be like, for example, two persons, they are trying to hold a conversation at a greater distance. Now, suppose or consider the same situation in a noise party. If everybody shows at the party, or everybody shows in the broadcast terms, in the radio terms, all this will use the battery energy even more rapidly or very quickly. The battery energy can be used out. So a method would be speak more slowly and speak more clearly. So that's the job of spreading factor. Spreading factor can help you to send a message at extreme distance successfully. A spreading factor indicates the number of the data bits per second, the payload per time unit. So LoRa modulation has a total of spreading factors from SF7 to SF12. The bigger the spreading factor used, the larger range, the bigger distance, the signal will be able to travel and still be received by the receiver without any problems. And here, be mindful is a very important orthogonality. That's another very professional term. We can easily understand. Well, spreading factor, they are invisible to each other. They are in relative to each other. This means that signals modulated with different spreading factor and transmitted at the same time, on the same frequency, on the same channel, simultaneously, they do not interference with each other. So, spreading factor, they are invisible to each other. That's the orthogonality. Okay, here you can see in this picture, okay, the color in the orange, that stands for the gateway station, the LoRa 1 station here. So the distance increase, well, the distance increases, the signal is sent with the spreading factor stepping from 7 nearby to 12 at a distance. So you can find a relationship between the spreading factor and the range. The higher the spreading factor, the bigger range that you can arrive. And if every communication was just allowed to follow this same pattern, I mean, the whole network will be slowed down. So in order to prevent this situation from happening, there is another regulation, there's another rule that is the limits the total amount of time that any transmission can take. So this is just 1% of the total allowable time. This time limit is the duty cycle that happens in European countries, in European region. So later we can discuss more about the duty cycle, but in order to maintain the whole network speed, so there are duty cycle restrictions. And the short range communication speaking rapidly, So it can pass more data at a higher data rate against to the distance extremes. So here you can find that a higher spreading factor, the smaller payload size. And this trade-off of distance against power transmitted and the quantity of data sent is covered by the heading data rate that ranges from 0 to 6, so 0 at the extreme and 6 nearby. And I think understanding this feature of LoRa is quite sufficient for us to understand the bit rate and finally later the receiver sensitivity. So here we can simply to remember that a lower spreading factor, it means shorter range, smaller range, and the less time on air, but you can use smaller or less lower energy consumption, and you can extend your battery life, of course, but you can send the higher data rate, so the frequency to send data is much higher, so you can send a little bit more data maybe. And this is a table that tell you the uplink, especially for the uplink messages from SF7 to SF10. And the relationship between spreading factor, the bit rate, the range, and time on air. And time on air is another restriction for the FCC that authorized in United States. So what the spreading factor to use, which one can be used, this is always your choice. You can decide by yourself, but no single spreading factor is always best for your whole solution, for your use case. That is why LoRaWAN has a mechanism that called adaptive data rate mechanism. The adaptive data rate is choosing the best spreading factor in a particular scenario, For example, when the sensor nodes they are close to the gateway, they can use a high data rate, the lower spreading factor, so they spend less time on air to transmit payload, to transmit data. And for more distant nodes, for the sensor nodes that are far away from the gateway, so the data rate is lower, so higher spreading factor, and the link budget is higher as well. And based on the exact situation, the network can tell the end devices to change the data rate, and that is really powerful in LoRaWAN because you can automatically and dynamically to change the data rates, to change the spreading factor, and optimize so as to optimize your battery life and the link quality. And I think you may be curious why the network can figure out what is the optimized spreading factor for the end devices. Now, in order to clear about that question, we need to figure out how network server works. Well, let's see same diagram, see this topographic. First, the end devices sends an uplink message through the gateway, right? So the gateway here is just simply pass the message to the network server without any processing, without acting on the data. So the dump gateway is a LoRaWAN network. In a LoRaWAN network, the gateway only converts the LoRaWAN packets into IP packets and sends that IP packets securely through internet to the network server through the backhaul connection, such as through the wireless, like 4G or 3G or even 5G, or through Wi-Fi, or through the wired cable, Ethernet cable, or sometimes through satellite to the network server. Anyway, gateway here is just to bring an IP connection. So this IP packets include a small amount of metadata about the reception time and the signal strength. That's very important. So according to the strength of the received signal, the network server determines what the best data rate should be and what is the what's the optimal spreading factor should be used by the end devices. So the network server sends a mark comment to the end devices based on the global view, based on the overview of the signal, stress signal from all gateways. So there is the ADR mechanism, ADR settings on the end devices. If you enable this ADR settings in the end device will accept the command and try the suggested spreading factor from the network server. But if you disable it, end device will reject this suggestion, will reject this command, will only use the original spreading factor that you manually input at the first beginning. So, generally, the ADR mechanism is strongly recommended to be enabled in the end device. If your devices, if your sensors and gateway, they are deployed in a place for a long time, they are in the static state, not in the moving station. Okay, it's not the sensors, they are not installed such as in the cars or on the trains that always keeping it moving. So in that case, you can enable this ADR mechanism. But if your end devices, is always keeping in change its distance, keeping in change with the distance between to the gateway. For example, if your sensors, the LoRa based sensors, they are deployed in the buses or in the asset tracking for the tracking applications, or if your LoRa sensor is the parking sensor, that a car is parked above your sensor, that you don't have the sufficient radio frequency strength. So in that case, you can temporarily disable this ADR mechanism. Okay, otherwise, please, it's better to enable it. And LoRa is the unlicensed spectrum, so it also has something about limitations that you need to consider. For example, the duty cycle or dwell time. It means the certain amount of time before the signal received by the receiver. So it differs from region to region, country to country. For example, in Europe, you have the duty cycle that is 0.1% to 10% duty cycle per day, depending on the channel. So to respect the 1% duty cycle, for example, after sending a message, we have to wait about 52 seconds before sending a new message. So these restrictions are various in different regions. And in United States, you don't have the duty cycle, but you have the dwell time. It means 400 milliseconds per channel, and you have 34 channels totally. And basically, in MileSight, all our LoRa devices, the settings, this settings has been fixed. The settings has been fixed in order to respect the duty cycle and the dwell time restrictions, because there are legal requirements that required by your government. So the end users, they are not allowed to change the duty cycle in Europe, for example, and neither in United States. And besides the legal limitations, you may probably have some other limitations as well. For example, if you'd like to take use of the service from the public network provider or from the third-party network server provider, then you may have the payment plans for sending messages per month or per quarter or per year, it depends. Or if you have take use of the service from TTN, for example, there's a fair access policy that limit the numbers of uplinks and downlinks per node, per end device per day. So you need to respect these restrictions from TTN as well. But you don't need to follow up this restriction for building up a private LoRa WAN network. For example, if you have a smart office, well, you build up a solution for smart office monitoring, you can purchase the sensors from outside, purchase the gateway, LoRa WAN gateway from outside, and our gateway comes with the embedded network server that service in the gateway hardware already. So you don't need to take use any third parties services to build up your own private LoRa WAN network. Then in that case, you don't need to respect the restrictions. But you still need to respect the duty cycle and the dwell time. So the range, that's one of the key benefits of LoRa. So free space path loss tells you how much energy is lost in free space between transceiver and receiver. So understanding free space path loss will help us understand how far a LoRa signal can go. So this FSPL is not specific to LoRa waves. It can be applied to any other waves, such as Wi-Fi, for example, using other frequencies. So here you can find our free space path loss is a formula, and it takes into consideration of the distance between the transceiver and the receiver, as well as the frequency. If you Google online, you can find two different formulas. The difference between them is the unit. Well, if the frequency unit is in hertz, so you can find the formula is minus 147.55. And if you frequency is in the unit is in megahertz, so you can find the formula with plus 32.44. So that's the only difference between them. And receive power. Well, it's very important to figure out the receive power. It equals the transmit power. It means the transmitter used to transmit the energy. That's the minimum power it must use. So the transmit power plus all the antenna gains of both transmitter and receiver, and minus the connector loss of both transmitter and receiver side. And why we need to figure out the receive power? Because we need to make sure that the receive power is higher or bigger than the receiver sensitivity. Otherwise, your message may get lost in space. So the receiver sensitivity, it needs to be as low as possible. Or the range between the end device and the gateway should be short enough to receive the message. So with this formula, you can figure out the receive power. Here, what we are pursuing, what we are need to make sure is our receive power is definitely higher than the receiver sensitivity. So the receiver sensitivity is also another formula. We need to make sure, as we mentioned, that receiver sensitivity is lower than the receive power. So it takes the signal-to-noise ratio, the detection bandwidth, and the noise figure, and the thermal noise on the room temperature, all these factors into consideration. So here you can find some other technical terms. Bandwidth is bandwidth. Well, the SNR limit, it means the signal-to-noise ratio. It means the minimum ratio of wanted signal power to noise that can be demodulated. And the noise figure, it depends on what type or which model of the LoRa chipset that you are using. So it's fixed a figure that determined by the hardware, that determined by the chipset. And the noise floor, that's very important. As we already mentioned, we can simply understand noise. Noise floor is a place where it's full of unwanted interfering signals, which can corrupt, which can destroy the transmitted signals. And here you can find a table that is the SNR limit can be found by the spreading factor. So every U plus spreading factor plus one spreading factor, the SNR limit is plus minus 2.5, okay, 2.5 dB. So we can find out our signal to noise ratio limit according to our spreading factor, and the typical LoRa SNR values are between minus 20 dB to plus 10 dB. Okay. And so anyway, that receiver sensitivity formula you can figure out it and compare with the receiver power. And link budget. Link budget is a way of quantifying the link performance. So 3 different factors can determine it: the transmit power, transmit antenna gain, and the receive antenna gains. So you can see in the picture here, everything what is in green color, there are gains, and everything what is in yellow color, there are losses. So link budget, it determines the range, determines the distance. And if that power minus the free space loss of the link path is greater than the minimum received power, then a link is possible. So you can make sure that your message can be received successfully. And here is our example with 125 kHz bandwidth, and is the typical bandwidth used in LoRa communication, and the highest spreading factor, SF12, and we can know the signal-to-noise ratio. That limit should be minus 20 dB according to the table on the last slide. And the noise figure, here we can suppose that use 6 dB. Okay, noise figure is the characteristic of the end device, so is the typical figure. And then when the transmit power uses 14 dBm. So can you figure out what's the receiver sensitivity and what's the link budget according to the above 2 formulas? Well, here is the answer. You can double check with your own calculation. The receiver sensitivity is minus 137 dBm, and the link budget equals 151 dBm. So here, if we can see from this picture, you have the transmit power here. On the top left is the 14 dBm, and you have the receiver sensitivity is minus 137. That's lower than the received power here. And also that gives you a link budget of 151 dBm, the link budget. So what does that mean? What does 151 mean? If we compare it, we compare with other wireless technologies. In Wi-Fi, for example, the transmit power is much higher, so it needs more battery. The receiver sensitivity value is also higher, so that means your link budget is smaller, so it's 95.5. And LoRa is 151, right? If we do the same calculation for the narrowband IoT, for the NB-IoT technology, it has a similar link budget that is 152. It means similar distance. But you can see here that LoRa can reach a very similar budget, a very similar distance as NB-IoT, but with much less transmit power. It means less power consumption. So this is just the calculation skills on paper. If in fact in our real deployment, 8 times more power for the narrowband IoT. So it means 8 times more power to get the same distance as LoRa. So if you need the long distance and smaller energy consumption, LoRa is much better than NB-IoT. So the link budget equation and path loss, you can know how much path loss on the radio link you can afford, but still having a reliable radio link. And resolve the path loss into a physical distance. It will give you an idea about the coverage area that you can expect. And let's see some theoretic value and the real limit in practice, or what is the real range that you can get with LoRa. And some people already tested through setting up the senders and receivers on mountains, on top of mountains, and they get data over hundreds of kilometers range. And theoretic maximum value is about 850 kilometers with the free space loss algorithm, calculation. And TTN, the Things Network community, did a real test on 2020, on last year. They put a transceiver with a big helium balloon here. You can find this very big balloon in the white color here. So the transceiver is about 14 dBm, or 25 milliwatts of power. And the transceiver moves on a very high space. It means there are about 36 kilometers of the altitude from the ground. So it supports the European frequencies. It's the European frequency testing European regions. So it kept sending the transceiver. It kept sending the messages out from the balloon. And guess what? The message finally arrived at a gateway in Czech Republic, and there is about 332 kilometers between the transceiver and the gateway. Well, you may ask, since LoRa can support the range of hundreds of kilometers, can we use one single unit of gateway to cover all Europe or cover all Australia? And that's obviously no. The answer is no, because free space is only in space. And on the Earth, we have factors like the structure attenuation, like the buildings, the trees, the materials, things like that. There's reflections and diffractions. So there are buildings with a lot of glass that reflect the radio frequency signal. And also there is a Fresnel zoom. So if you have the ground, if you have the hill hilltop or mountaintop or the building within that Fresnel zone, well, it's definitely influence the signal strength. So you must have a lot of straight line of sight paths around your devices to ensure the communication quality. So your range is limited. Your range is shortened by all of those kind of factors. The reflection, diffraction, Fresnel zoom, and structure attenuation. And in a typical wireless environment, there is not a direct line of sight path between the transceiver and the receiver. In fact, the radio wave from the transmitter will take different paths, will take different ways to reach the receiver. It depends on the obstacles in the environment. It depends on the barriers in the environment. So the multi-path phenomena will result in the interference. And according to the experimental testing, the LoRa has a very high immunity to this kind of phenomena, especially in the low data rates, the higher spreading factors. So that's why you can find why LoRa is so suitable, is so perfect for the long distance data transmission to resist to this kind of interference. And if you always enable the adaptive data rate mechanism, or if you deploy the gateway that close to the sensors, that would be helpful as well. That would be help the devices to resistant to this kind of interference that caused by the multi-paths. And finally, another physical aspect that is important to take care, that is the Doppler effect. I think you can still remember the sound changes when a police car, when an ambulance, 911, that passing by. I think that's the same with this LoRa, when an end device that would be moving really fast away from a gateway or moving really fast towards to a gateway is changing the frequency. So, and LoRa has proven to be super robust against this Doppler effect. And that means you can also install the LoRa devices on the moving objects, such as the cars, the buses, the trains, for the asset checking or the cold chain monitoring. Okay, those kind of applications we can still take use of the LoRaWAN based devices for the moving object. And what are the considerations for big range coverage? Well, it's always better to install the gateways outside, in the outdoor, in the open space, and on a higher altitude. And that's quite some testing has approved this result already. So, and if you ask me how many kilometers that your mile-side gateway can support, well, it's very, very difficult to tell you the exact number because it depends on so many different factors from both environment and from the devices themselves. So the range depends on the indoor-outdoor placement as well as the position of the gateway and also the position, elevation of the end devices. So here, if you need to cover the big range, big distance, please make sure where is your gateway and end devices deployed. And summary of LoRa, you can enjoy the long range, you can enjoy the long battery life, and easily expand the network capacity by adding more devices or adding more gateway. So it's so robust to the electronic magnetic interference, and the multipath fading, and the Doppler effect. So LoRa can be a real choice, real good choice for IoT applications. And LoRa is a radio, not a protocol. So next time we are going to talk about something related to LoRaWAN. If you ask me, is it very safe? Is it safe to transmit data over the air by using LoRa? Well, I think it's similar asking me a question like, is it safe to use this car? Is it safe to work on the road? Because it totally depends how you drive the car and how you work on the road and whether you can respect the traffic regulations. So that's what LoRaWAN does. That's the job of LoRaWAN. So next time, let's talk a little bit more about LoRaWAN. So thanks very much for staying with me until the last slide. Hope you can enjoy this webinar. So see you next time. Bye bye.